Okay, so in the last lecture, we did the Theorem models where we assume that yi looks like this, where each y is a function of the parameter space beta with an error epsilon I, which is random with mean 0 and variance sigma squared and uncorrelated. And such a model is called linear model. And the reason for linear model is the fact that you could rewrite the model as the mean of yi's being a linear combination of the beta i's, unknown parameters, but the yi's are uncorrelated random variables with variance sigma squared as another way of representing model. And since the mean is a linear function of the betas, it's called a linear model. Okay, let me give some quick examples, and then I'll sort of start some understanding of this particular model set. So one example is we already seen in the beginning of today or this week's class is the one-way classification model. So it's called the one-way classification. So in this model, the particular beta i's and the xi's form a certain collection. Like so, yij was equal to mu plus mu I plus epsilon j. So, and then here we had, like we said, 1 less than equal to I less than equal to k populations, and j was n samples when each of them was ni. This is a one-way classification. Another example is called a nested classification. So here you do a triplet. So I'll explain in a second. Nested classification model. So here you have yijk was equal to mu plus mu I plus delta ij plus I'll have epsilon ijk. Okay. And here 1 is less than equal to k less than equal to nij's. Okay. I'll have 1 less than equal to j less than equal to ni. And I'll have my ik populations, 1 less than equal to I less than equal to k. So it's kind of nested. So you have k between 1 and ij's, j between 1 and ni's, and 1 between I and k. The last one is what's called a three-way classification model. Here what happens, here you have yijk is equal to mu plus alpha I plus beta j plus gamma ij plus epsilon ijk. So randomness is only in the epsilon, everything else is a parameter. So here 1 less than equal to k less than equal to nij. I'll have 1 less than equal to j less than equal to capital J goes independently, and y also will be capital J. Or maybe capital I, I'll just call it some different one. So it's called three-way classification. And what's unique about this is that all models, as discussed before, all models can be represented as y, which is just y1 to ym. So in matrix notation, I'll call it y1, y2, all the way to yn, whole transpose. I'll have beta as beta 1, beta 2, beta m transpose, and I'll have x as some xij. So here 1 less than equal to I less than equal to n, and 1 less than equal to j less than equal to m. And I'll have epsilons, my epsilon tildes, right? I call this y tilde at the bottom. It will be again epsilon 1, epsilon 2, all little epsilon n transpose. And my model is y is equal to x beta plus epsilon. So Y is an n cross 1 matrix. So we call the Y is an n cross 1 matrix. X is a n cross m matrix. Beta is an m cross 1 matrix. And epsilon is a n cross 1 matrix. So, and then you could think of it as, you could think of epsilon i's, the epsilons, having a variance covariance matrix given by sigma squared times identity. So, and typically one thinks of the model in this following form. What are your parameters? Your parameters y, your x beta is important, that's the thing, and then sigma squared in is what you. So from our earlier work, we know that y is the observation vector. X beta is the mean of y, and sigma squared is the variance of the variance covariance matrix of the y vector. Variance covariance matrix of the y vector of the data. It's another way of representing the model. So it's concise way of writing it. We let y, x beta, and epsilon. So of course, some people have a notation for the vector like x beta like this, or beta like this. Very nice. So let me go back and make, sorry, double a little bit so I can see both sides. In one shot, make two windows and review a little bit. Go back here, open this up. Very nice. So the examples I discussed: the one-way classification model, the two-way classification model, and three-way classification model, and all these are part of the linear model setup that I discussed above. And then all models can be represented by this form. So by this form that y is equal to x beta plus e, where e is there, and x is some suitable matrix with known constants, beta the parameter set, and epsilon. Or you could just think of the three key parameters, y, x beta, and sigma squared n. But y is the observation, x beta is the mean, like I came from here, and sigma squared is the variance covariance matrix. So now let me come to the, I have this particular model now. Let me go back and address the first question that I started off with. What is the idea? What all can I estimate? Where can I go from here? So let me go. So this is now, I'll go into what's called the problem of estimation of the parameters. So what do I have? So let's take, suppose I have y, I have x beta, I have y, I have x beta, and I have sigma squared I, be a linear model. Sorry. The parameters are you have a beta m cross 1 vector and sigma squared. They are your two parameters, right? That's what you wanted. So I can think of this whole thing as sigma squared is positive. So I can think of it parameter space as belonging to, so Rm is where the beta lives in, and R plus is where the sigma squared lives in. So that's the parameter space. So I'll think of it as parameter space, like in a capital theta as a parameter space. That is the parameter space is. So belongs, so I'll just say is. is in the space. Okay. So now let's try and see if I remember. I go back to the original example. I had this mu1 minus mu2 in the beginning of identifiable. One knows that I can't estimate everything because of this idea that I explained in the first lecture of this week. So here, let's try and estimate linear functions of the parameters. Okay. Okay. So what is a linear function parameter? Let's define that first before we start doing. So for any P in Rm, a linear combination. So here P is a linear a vector Rm. So I'll think of it as P1 beta 1, P2 beta 2, all the way till Pm beta m. Right? This is just going to be P transpose beta. Right? That's the definition. Right? So I take the vector P transpose it, multiply beta. Right? A linear combination P times beta of the parameter beta vector beta is called. So any linear combination is called a linear function of the parameter. Okay? So I'll write a little differently. I'll call it linear parametric function. Very good. So this is something I'll now fix as my sub problem. So I'll just note right now for once and for all. In a linear model, we'll be interested in only in linear function parameters. So only in linear parametric functions. Okay. That's the first thing. Okay. So take linear model. I only want to estimate linear parameters. So first, now once I decide this is going to be my objective of defining of understanding the linear model, I only want to estimate linear parametric functions. I have to go about telling how to do it and what all I can do. Okay. Let me go back and let me try and do that. So here's the definition. Suppose y x beta and sigma squared I be a linear model and P in Rm, P be in Rm. So you have two things, a linear model and a vector P in Rm. The linear parametric function is, so what's the function? The function is P transpose beta is said to be estimable estimable if, so the key thing is, so when can I estimate this P? When do I call it estimable, right? So if, the idea is that if there is a vector L in Rn such that I take a linear combination of the y's, that is L transpose y, a linear combination of the y's, its mean should be the same as P transpose beta. So that is, let's say, a little bit fancy words in early statistics is the following. That is, in other words, there exists a vector L in Rn such that L transpose Y is unbiased estimate of P transpose beta. That's the first definition. Let me make this double. So I have the linear function parameters. I say estimable if there is a vector L in Rn so that L transpose Y is an unbiased estimator of P transpose beta. So that's when I call P transpose beta estimable. Very cool. Now here's the first theorem of the class. First theorem of the class is following. Let y, x beta, and sigma squared in be a linear model, and P be a vector in Rn. That's the first thing. Then P transpose beta is estimable if and only if, so it's very important. So what's the definition of estimable? There's a vector L such that L transpose Y is an unbiased estimator of P transpose beta, right? But the condition is that I have a linear algebra condition, P transpose beta estimate, if and only if P is in the column space of X transpose. So that's just so what does this mean? This definition where column space of X transpose is just the set of all, let's say, call it set of all Z, such that there is a Y, X transpose Y is equal to Z. So only when P is in the column space of X transpose can you get P transpose Y beta estimable. This is a sort of a nice theorem. The proof is also not is very doable. Let's do the proof, and then we'll come back and sort of pose the problem. So what's the proof? The proof is fairly elementary. So let's start with it. Let's say P transpose beta is estimable. Right? That's what we start with. When is it done? That means from our earlier definition, if you go back up, that means there is a vector L such that E of L transpose Y is P beta. Let's copy that. Let's put that down here. This happens. So we make it a little smaller. So okay. And that's if and only if you look at it carefully, there is an L in Rn such that, so what's critical now? What is what is E of L transpose Y? That we know is same as X beta, right? And L transpose is L transpose Y. E of Y is X beta, so E of L transpose Y is just same as L transpose X beta, right? Because by linearity expectations, right? The same as P transpose beta. So how did I get this? I got this line by linearity of expectation. Very cool. And that's if and only if what happens, there is an L in Rn, right? So this is true for every beta, right? This is true for every beta. So I should just state the theorem properly. I think I did it correctly. Let's say a beta is any Rn, this is true for every beta, right? So it's true for all beta. Because you don't know what beta is, right? This is true for all beta. This is true for all beta Rm. If this is true for all beta Rm, that means just a simple way of writing it, does X transpose L is equal to P transpose, right? Because if this is true for all beta, this has to be true. Because if this is not true, this will not be true for all beta. A simple fact, a linear algebra fact. So I'll leave it as X linear algebra. But that's the same as saying that P is in the column space of X transpose. Nothing else. This should be as P here. Sorry. That's it. Nothing else to be done. Very cool. So I may put the other things for vectors. I have not done that consistently. Very cool. It's a simple proof.